Okay, well, I hope everyone is enjoying or has enjoyed their holidays, depending on what time it is when you listen to this. Um, but I want to talk to you a little bit about energy and work. So to explain these, I think the best way to do it is just sort of dive right in and start talking about the history of energy. Because these sort of get defined in circular ways. Work gets defined in terms of energy, and energy gets defined in terms of work. And if you just read definitions, it's kind of hard to understand what they're talking about. So the history of energy basically is that the quantity mv squared, um, people have sort of looked at that over the years, and for several centuries people noticed that in a lot of physical systems this was conserved. So if you had a bunch of objects with different masses, and they had different speeds, in whatever direction, you could basically take all these objects, for each object take its mass times the square of its speed, and then add it all up for all of them, and that would be conserved for this system, even when these objects would collide and things like that. Um, Sometimes, but not always. So this was called, by the people who investigate, they called it vis viva, which I guess is Latin for, the energy, I don't know, something of motion, but whatever this means, you Latin nerds can tell me. And so some people thought that was sort of the fundamental conserved quantity in nature. And then, of course, you remember we've dealt with mv, mass times velocity, which is momentum, and some people thought that was conserved. So there was this, sort of fight for a while between the mv squared people and the mv people about which one was really sort of the El Primo, quantity that explains everything and is always conserved. And momentum ended up sort of winning out in the short term because Isaac Newton, sort of championed momentum and showed really that momentum is always conserved. It is only changed when a force acts. So the whole mv squared thing kind of fell into disrepute for a while, but eventually some people sort of looked at it again and realized that this is still conserved. It's just you have to do a little more explaining, and sometimes it gets changed into other forms. It seems strange, I know, to think that, well, we just spent a couple of weeks telling you about how mv is conserved. Now we're telling you that mv squared is also kind of conserved. So let's the best thing to do is really just sort of dive into this and start talking about it. So let's look at how mv squared changes. So say we have an object here, with a mass m, and it's got some speed v0 at some point, and then later on still has mass m and has some speed v1. So how can we relate these? And more importantly, if we're looking to do it in terms of this mv squared, really how can we relate the squares of these speeds, right? So, and these might be in different directions, but let's start with a one-dimensional case where it's going in the same direction, and it just moves along, along one dimension, which we'll call x. So it's moving along x. This is positive x, and let's say it moves. Say this is 0. It starts at position 0 and ends at position d. Okay, so it moves through distance d. How can we relate these two? Well, if we go back to sort of one-dimensional kinematics and some of the fundamental equations there, you'll remember one of the equations we dealt with was v final squared equals v initial squared plus 2 times acceleration in the x direction times the change in x, right? This was one of our fundamental ones, and we could do this in y or z if we use the y or z components, but for here we're just going to use the x because that's our one coordinate. So great, so let's try to apply that here, and what we can do is our initial, our final here was v1 squared, so this is time, it's at state 1 we can call it, and this is state 0, so going from 0 to 1, v1 squared is our final velocity, v0 squared is our initial velocity, and then 2 times the acceleration we had. I'm just going to leave it as a instead of ax because we're only dealing with one dimension x. And then how far did we travel next? We traveled this distance d. Okay, so, and Sydney, my cat, is coming out to join me, so she's going to be sitting in my lap, so I'll be trying to keep up for a few minutes. So anyway, so here's a relationship, and you'll recall that what's required to make this work... Okay, Sydney, you just sit down there. That's great. Or sit down there. No, you're not drinking my... Damn it. Sydney, no. Sydney has this weird thing. She likes to drink water. I had a glass of water sitting there. On the end table next to me on the couch, so she wanted to go drink the water. So now I've rescued her from her. Maybe now she'll settle down my lap. Anyway, sorry about that. So the condition that has to hold for this equation to work is that acceleration has to be constant. Remember, this was an equation we derived specifically under the assumption of constant acceleration. Okay, so so we're going to have to remember that we have to have constant acceleration for this to work. So what can we do now to get this mv squared quantity out of this? Well, it seems pretty obvious. We just multiply this whole equation by m, right? So let's do that. And we get mv1 squared equals mv naught squared plus 2 MAD. Okay, so there's our mv1 squared. You can think of this as the vis viva at point 1, right? Okay, and mv naught squared, which is the vis viva at point 0, and then 2 times ma times d. Okay, so that's okay. And let's change this slightly to be final vis viva, or vis viva at 1, minus vis viva at 0 squared. Okay, so it's mv1 squared minus mv naught squared equals 2 times ma times d. Now, what else could we do with this? Well, look at this in here. This last term here, 2 ma times d. What's ma? What did Newton have to say about ma, huh? Mass times acceleration is force, right? So this is actually the force acting on this object. So this here, ma equals F. So there's a force acting on this object to cause it to accelerate, right? A net force. And so we can say that force is equal to ma. So we can pull all this out here and say, come on, Sydney, settle down. She wants to sit on my lap, but she's sort of wandering around trying to find a good spot. Okay. Anyway, so now we can say mv1 squared minus mv naught squared equals 2f, this is ma, right, d. So now we have something very nice. The final vis viva of this thing minus the initial vis viva of this thing. So the change in this thing's vis viva is equal to 2 times the force acting on it times the distance it traveled while that force was acting on it. Now remember that this comes from this equation here, and the condition here was that a was constant, and F equals ma here. So the condition here, so this is sort of the condition for this thing. The condition here was that F is constant. Okay, so this equation works for constant F. But that's all fine. Okay, so the only thing really left to do to this is some people looked at this at some point. I think some French scientists, in the 1800s or 1900s, 1800s actually, and they said, look, we could either keep it like this and have this 2FD here, or we could multiply everything by 1/2, and then just have FD and have 1/2 mv squared. You know what? Let's multiply by 1/2, they said. Or they were French. They were, let us multiply by 1/2 to change the numbers a bit. So, we will divide everything by 2. Would you like some wine? Okay. So, or I assume they had some wine after they finished dividing everything by 2. So then we come up with 1/2 mv1 squared minus 1/2 mv0 squared equals, and then divide this by 2, FD. And so this now is just the change in this quantity 1/2 mv1 squared. So change delta of 1/2 mv squared. So the change in this quantity equals the force acting on the object times the distance over which the force acted. And now this is actually exactly what we're after, energy and work. This quantity here on the left is, believe it or not, or this quantity in here, in this parentheses anyway, is kinetic energy. This is something called kinetic energy. And kinetic energy is the energy of motion. And this quantity on the left here, FD, is something called work. So in the physical sense, work is the change in kinetic energy. So let's tell you, I'm going to sort of do this over here in a corner. I'm going to draw a little box. And what we're going to say is work equals the change in kinetic energy. And I'm marking kinetic energy with this E, capital E subscript K. EK is 1/2 mv squared, and work is force times distance. This is for the case, so let's make it clear, this is for the case where we have a constant force. And this is all one-dimensional still. So this is sort of very preliminary. We're dealing with a constant force and a one-dimensional system. This is going to get fleshed out more when we do other more general cases. But for now, this is sort of our first stab at a relationship between energy and work. And this is what came out of this whole idea of vis viva. Kinetic energy, which is just 1/2 of vis viva. And kinetic energy is what we use now. So we'll talk a little bit more about how these work together in the next video.